Welcome everyone to this edition of Verifiability Talk. Just a notice, this meeting is being recorded and later will be made available on YouTube, on our YouTube channel. So if you don't want your name or initials to appear on YouTube, you could log out and log in as a guest with a different name or with something that you don't mind being shown on YouTube. Otherwise, it may happen that if you ask a question, your name or your initials may show up later on in the Teams window and hence later also in the YouTube recording. With that in mind, it's my honor and pleasure to introduce today's speaker, Jan Peleska. Jan is someone who has been doing a lot of very interesting research in model-based testing. He is someone who likes foundational research, but also likes applying that to very challenging scenarios and systems. And he does not compromise the importance of rigor when applying those ideas in practice. He has been working on model-based testing for a very long time. He's a professor at the University of Bremen, but he's also involved in a very successful company called Verify Systems International. Jan, thank you very much for having accepted our invitation, and the floor is yours.
Thank you very much, Mohammed. That was a very kind introduction. I have the honor and the pleasure to talk about our new research project called HyDive, Highly Dynamic Virtual and Hybrid Validation and Verification. Perhaps for the title, it should be mentioned, hybrid has nothing to do with hybrid systems in the computer science sense, but more like mixed validation and verification where you use original equipment, for example, for hardware in the loop testing combined with simulations. So that's the term hybrid in that sense. And compared to the trustworthy autonomous systems project that Mohammed and many others in the audience are working on. This is a small project. There are just 4 members. Airbus is the project leader. DSpace and Verified are industrial participants. Both are experts in the field of embedded systems testing or cyber physical systems testing. And the University of Bremen has the role to provide the, let's say, solid scientific foundation. So I think that describes what it's all about. And now, what I would like to tell you about today, just a bit about the project objectives. But this tends to be very boring if I drone on and on about work package 1 and 2 and 3. Instead of that, I would like to focus on the second bullet point, a closer look on test-related V&V challenges. And then I will explain to you what we can solve very nicely from today's point of view and where I find the challenges where I don't know how to do that. And fortunately, your huge project and our small project are very nicely related to each other and complementary in some aspects. And perhaps you have solutions for me, or perhaps I have some suggestions for you that you find interesting. And then I will stop with a summary of research foci. We will see when we come to that. So the project objectives. They can be explained best by talking about 3 potential project scenarios about future developments in the avionic domain. These examples were provided by Airbus, and you will see from these examples that all of them are quite challenging as far as the V&V aspects are involved. The first is formation flight. This is quite similar to platooning of trucks, which has been thoroughly investigated in the field of automotive autonomous systems. So also with civil aircrafts, there is the idea that one aircraft can follow the other and save fuel by flying closely to the previous aircraft. And you can imagine that this is a completely change of paradigm. Up to now, civil aircrafts tend to avoid each other in the air, and now they have to look for each other and fly in a row as closely as possible. The other scenario is autonomous taxiing. That means driving on the airport runways, autonomous takeoff and landing. And as you might know from statistics, most accidents with aircrafts happen during takeoff, landing and taxiing. So this seems to be very challenging from the safety critical point of view. But the idea is to have your autopilot switched on when you are leaving the gate, and the aircraft is put onto the runway, and you are taxiing to that position automatically, and then you do automatic takeoff, and so on and so on. And of course, there still the pilots would be present. There is no idea at the moment that one would have autonomous civil aircrafts without pilots. That's not discussed today, but still the autopilot would take over another important portion of the pilot's work. And then perhaps the most future-oriented scenario would be that of urban mobility. On the right-hand side in this photo here, you see that Airbus and subcontractors have designed something called a passenger capsule. And this capsule can be glued underneath a drone or put on top of an autonomous electric vehicle. And so the idea is that passengers can drive autonomously through town, go to a parking lot. There they are taken over by a drone and transported through the air onto the top of one of these skyscrapers that you see in the background. And as you can imagine, there are loads of different scientific challenges, of certification challenges to get things like that certified. And now I'm coming to the main part of my talk. Let's see what's so difficult about that. And perhaps afterwards we could have a discussion that you have solutions for me, or you can challenge whatever I said might be a good solution. Let us first remember that all of these scenarios somehow involve artificial intelligence. All of these scenarios involve machine learning, so that the drones optimize their flying behavior, the aircrafts flying next to each other optimize their fuel usage, and so on and so on. And then you look at today's standards. This is the railway standard, the 5128, and they say the usage of artificial intelligence algorithms for any purposes, here it's fault correction of a control system, is not allowed. And we know the many reasons for that, but this is actually changing. There are loads of scientific papers published at the moment how some sorts of artificial intelligence applications and algorithms can be used and still certified in compliance with today's standards. Or there are publications how the applicable standards should be modified in order to allow for these novel application types to become certified and to become operative. This slide might be important if you go to sleep afterwards, because these are the main challenges that I see today. And later on, I will give you a concrete example about some of these challenges. But as a summary, I think this slide is quite important because all our work packages are streamlined along these challenges. This is what Airbus and their partners are working on. The first is a very general observation. Today's applications, even if they don't have anything to do with artificial intelligence, they tend to become so complex that we expect that they can't be fully specified in one comprehensive model anymore. And I'm convinced that applications, even if they are outside the autonomous systems realm, they will be specified in the future just as autonomous cars by catalogs of scenario models. So during the specification and design phase, there will not be compiled one centralized model which we think is comprehensive, but instead there will be a catalog of scenarios. And each scenario describes a specific operational situation. And this situation is then completely and fully formally described. But of course, then you have to worry about methods, how to verify the completeness of your scenario catalog and the consistency. And so this seems to be a trend that cannot be avoided. Some people in the formal methods community challenge that statement, but we see that every day with our customers. Nobody is able to set up a complete model covering every aspect of the system to be developed, but instead they say, in this situation, this should happen, in another situation, another thing should happen. And so we are worried about the completeness of scenario libraries. Another thing is more closely to these applications that I have shown you on the previous slides. Systems of the future will evolve. They will change their behavior over their lifetime due to learning and behavioral optimization, and due to the execution of novel tasks by means of collaboration. The second bullet point deserves a bit more of explanation. We all know by means of machine learning, the behavior is optimized. But this, from my point of view, tends to result in approximately the same behavior that we had before, like applying a filter to make a robot movement smoother than it was before, but it's still similar to the previous movement. But with applying agent-based artificial intelligence algorithms, you can have new sorts of collaborations. Two drones might meet at a parking lot and decide that together they could carry a very heavy car or a very heavy load. And for that, sorry, somebody is making a really loud noise. Is that myself or is that somebody else?
I will look it up, and if there is any noise, I will mute.
Okay.
Yes. Mm-hmm.
Okay, but you should just switch off your microphone. Okay, and so by means of collaboration, which in particular means by stepwise elaboration of novel plans and exchange of plans, you can dynamically find a way to solve a new problem. And this, of course, leads to a completely new behavior that has not been anticipated during type certification. And this is where we think the real cruel challenges lie. And this leads to the necessity of runtime certification. I think this keyword came up a couple of times. I remember in one of Jim Woodcock's talks and in other places. So there will not only be a type certification, and that will not be valid once and for all, but instead runtime certification will become mandatory, so that when two autonomous systems decide to work on a completely new task, they exchange plans and they will they will then somehow become certified in addition to the type certification to perform this specific task. And I have some ideas about that, and of course other people are publishing about that already. And but still, it's one of the biggest challenges that we have, and therefore we have a work package that says we should talk to the certification authorities and work out future certification paradigms. The final challenge is the number of test cases will increase dramatically. In the automotive industry, that's an accepted fact already. There was an interesting publication. I think each of you knows that already. If you would test all the important test cases for an autonomous vehicle on the target hardware, and you have a fleet of 100 cars, it would take you more than 100 years to do the type certification. And so, of course, that won't work. And therefore, somehow cloud-based testing will become state of the art. And how can we get certification credit for tests performed in the cloud? We need virtual prototypes, that is, kind of simulators that are trustworthy in the sense that they model the complete memory map and all hardware details of the underlying machine. And then you can exercise a test in the cloud as if it was performed on the real hardware. And perhaps with that, you can get certification credit. So these were the 4 bullet points that we think in our project will get the main attention. And if you agree with that, you can simply go to sleep now, because now I will go into details what we can do with testing agent-based systems and what we cannot do at the moment. So I start with an example, what we can handle. And this example has been inspired by Kirsten Eder's talk. I think that was 2 talks ago. She talked about agent-based testing. But here I'm starting with a typical autonomous application, which is not too complex. And here I'm thinking first about an agent-based implementation, because artificial intelligence suggests that such a problem could be solved by an agent-based system. And so we are talking about a freight train that should drive autonomously from A to B. This is one of the problems that are really discussed at the moment in Europe. In France, they want to achieve by 2025, I think, that freight trains can autonomously interleave with passenger-based trains by 2025. And so the overall goal for this very simple example is to travel from A to B safely and reasonably fast. And we assume that this is a block that has been reserved for the freight train. So all the important, very complex problems that you might think of don't come in here at the moment. This block is reserved for the train. But this autonomous train gets some position sensor values. They come with a confidence value from each sensor. And from these different sensor values, then a position estimate is derived. And if the train is unsure about the position because it doesn't get position sensor values, or the confidence is very low, then the train should slow down. And if the train is sure about its actual position, then it should accelerate up to a maximum speed, and then it should still brake in time to stop at B with reasonable precision. So that's a standard problem. I think each of you knows that. And then we have the physical movement equations, how the speed changes over time delta if we have constant acceleration and constant deceleration, which means constant braking deceleration. And the position changes according to these laws. You know about that. The laws are not so important, just how an agent could solve that or could apply these. This is the main focus of my presentation, and then how we can test such a system, whether it works properly. And I'm saying this right at the beginning. What comes out of the what we can handle part is that a standard simple scenario of agent-based implementations can be translated into something like UML state machines. And then you can apply equivalence class testing. I will show that to you. And then we come to the part that we can't handle today, where the agents exploit all the possibilities of agent-based programming in artificial intelligence. And then all of us will become very afraid, and we have something to do research about for the next 3 years. Okay, so with the sensors, the idea is that in a monitoring cycle like 100 milliseconds, the controller will collect sensor values about the position, and each intelligent sensor delivers a position value and a confidence value. And then we can create a position estimate by saying the values, position values with low confidence are multiplied with the low confidence value, and those with high confidence with a higher value. And then we somehow normalize that and get a position estimate. And then we get an overall confidence whether we can trust this or not. And with these things available, the controller could work with a few decision rules about braking, acceleration, and coasting, where they just keep the velocity constant. So the rules could be like that. If our prediction, let us see that here, the prediction of the stop position is very important in railways. At each point of time, at each control loop cycle, we predict where we would come to a stop from the actual point with the actual speed where we are. So if the train is here, for example, it predicts when we would start braking now, where would we come to a stop. And if the prediction says we would really stop at B and not before, then we would start braking right away. And the control cycle is, of course, fast enough that we can detect that in time. And so that's the idea of X stop. And then we have rules like this. If the stop prediction is not yet at B, but a bit before, but this is very close to B already, then the rule should be keep the speed, but do not accelerate. We don't have to brake yet, because then we would come to a stop before we have reached B, but we would not accelerate, because then there's the danger to overrun our target point. Then if the position is unsafe, and we are faster than some safety speed, then we would brake. Actually, that's a real rule from the European train control system. If the automatic control breaks down because the train no longer knows where it is located, then the train engine driver takes over and is allowed to drive with something like 40 kilometers per hour or something. And so this is a be safe. And if the location is unsafe, but we are still below V safe, we could still accelerate a little bit. And in all other cases where we are not too close and the position estimate is safe, then we accelerate as long as we have not reached maximum speed. And then afterwards, we don't accelerate further and just keep the maximum speed. So this would be a very simplified but quite typical set of rules. And now we want to construct a BDI agent that implements these rules in an appropriate way. Here we would have formulas for that, but we don't have to discuss that. And before we come to the implementation, let's see how a testing environment would look. You might remember Kerstin Eder's presentation. She also had a testing environment where there would be agents throwing data at the system under test. And that's the same idea here. We would have agents simulating position values, and then we would have a test oracle checking whether the decision about speeding up or braking would be acceptable according to the present state of the system. So this is what we want to create at the end, such a testing environment. But before we come to that, we have to know how we can model the expected behavior of the BDI agent controlling the train. So what would be the beliefs of such a train controller agent? He believes in the position values received from the sensor with confidence. And so on each cycle, this belief would be refreshed. The old belief would in the old position would be discarded, and the belief in the new decision, in the new position and the new confidence would be taken up as a new belief. And I think this is redundant here. From these beliefs, we derive a new estimate. And of course, this is the sum of all the sensor values with appropriate weights. And then we would believe in the actual confidence value derived from all that. And then we would have a state of the actual velocity and the actual acceleration. You can see here, these beliefs are very close to conventional variables. And of course, you could program that in C++. It's just fun, for an example, to do that in a BDI agent language. And so the train controller agent would have plans depending on certain context situations to be carried out. And for example, one plan would be calculate the position estimate and its confidence value. And the syntax here is from JSON and agent speak. I found that quite simple to program, and there's a very nice book about that. And so I found that very educational for myself. And so what does that say? The agent has a plan that it wishes to start, that it wishes to evaluate an estimate for the actual position. Now, this plan is partial. It can only become operative if a certain context specification evaluates to true. In formal methods, we would say that would be a guard condition. But so it's a context. And so this says this plan is applicable when we have at least two sensor values available. So if the remote sensors gave us 2 position values, and then this is just syntax to get their confidence values. And if their confidence summed up is at least greater than 0. And then this plan becomes applicable, and we would estimate our position to this sum where we sum up over agent 1 and over to agent 2 multiplied by the weight value and divided to normalize that. And then we would come here to the confidence value as well. A plan is something that might become executed. Kirsten explained that very nicely in her talk. We have different desires, and for these desires we have plans. And then the desire is triggered and becomes intentional. It becomes an intention. And so here is an example where a new extension becomes active. After we have evaluated the position, we would say, now we want to forecast where the train would come to a standstill if we braked right now. And so this desire becomes now an intention. And the whole syntax looks like that. We have plans and plans and plans, and we have updated beliefs from the sensors. There's a bit different syntax for that. And then one would start with one intention and then update these intentions according to the operational state. Now, this is very simple because we have a fixed set of plans and we have a deterministic decision which plan becomes intentional. And as a consequence, we can represent that as a, let's say, reference model. Just a moment. So we could find a formal reference model that is just like a state machine or a hybrid system model or whatever you want to use as a formal model. So we could say what the agent should do is wait for the next cycle to start. Then comes an event, start of the next monitoring cycle. And then we branch for position evaluation. If we have 2 position values and their summed up confidence is greater than 0, then we go into that part that we had just seen on the slide. But of course, we would also evaluate some, let's say, emergency value. If we don't have anything from the sensors, or they say we have confidence 0, then one could make an estimate from the actual speed and the actual acceleration. And so this estimate would also have low confidence, but at least we can do that. After that, without any additional guards, we update the speed, we forecast the stopping position. And then again, we need guards to decide which of the acceleration plans becomes active. So we have plans for keeping the acceleration at 0. That means we will coast and not change the velocity. We have plans for braking and plans for acceleration. That is where we say the acceleration should be A+. This is where we are accelerating. And so we have guard conditions. For example, let's look at the lowest one here. That is the simple situation where we have not yet reached our target, where we have not yet reached the maximum position, where our prediction says we would come to a stop before our target position if we stop now, so we shouldn't. And the is safe predicate says the confidence is high enough to go to maximum speed. And so this is a guard condition. And overall, I have identified 9 states with 9 different context conditions where we have to make different decisions whether to speed up or to brake. But it's 9 states, but still it's a state machine. And now everybody from the formal methods community is happy because for state machines, we know how to test that. And the objective of the next few slides is to extend a bit what Kerstin Eder said in her talk. Her main result was if you give the agents selecting test cases in the environment some heuristics in the form of let's say, incentives, then the agents would produce better test cases. I completely agree with that. And I will now show you one of the strategies that we have worked out in the past, where we could direct the agents with even more precision than Kerstin had shown us in their talk. So the basic result of the next slides is take up Kerstin's idea from her talk and refine the incentive heuristics for the agents in the environment. And this will give you trustworthy test cases. So this is what I'm trying to work out now. And we will go just a bit into the formal stuff on the next slide. But first, let me explain what complete testing strategy means. A complete testing strategy is one that constructs complete test suites. A test suite is complete if it accepts every system under test conforming to the reference model. So it would never say this system is faulty if the system fully conforms to the model. And most important, it provides at least one failing test case for every non-conforming SUT. So this is one of the basics of and most important definitions of model-based testing. You wish to test whether your system under test conforms to your reference model, and then if you have a complete testing strategy at hand, then you can uncover every error and you will never reject a conforming implementation. This sounds wonderful, but of course, this only holds under certain hypotheses about the SUT, about the number of states inside the SUT, about the granularity of its guard conditions, and so on. And so in the end, your test suite will not lead to a formal proof, because you can't be certain about whether these hypotheses hold about your SUT. But the thing is, these complete testing strategies, they deliver extraordinary test strength. So even if your system under test does not quite conform about your hypothesis, the test suite that you have elaborated still will provide very good test strength and better test strength than heuristic test suites. And this is why I'm emphasizing that, and I will explain a bit more about that on the next slides. So this theory that we have elaborated a couple of years ago, it requires that you set up a special transition relation from your state machine model. And of course, the state machine only has one transition relation, but you can represent it, for example, in a disjunctive normal form. And you can distinguish between stable states where time passes and transient states which you leave directly. And this is such a distinction, and there's an algorithm how to produce a transition relation in that form. And then there's some nitty-gritty calculation how you can travel through sequences of transient states where no time has passed. So these are conditions enumerating the different transient paths through your state machine until you reach a stable state again. And from these conditions for transient paths, you develop conditions for coming from stable state I, this is where you are, to stable state J, where you come again to rest. And state here means system state. So it's not just the control state of your state machine, but the state of the control state vector extended by the value of the speed and so on and so on and so on. You will see that on the next slide. And all these things can be nicely automated because otherwise you would get desperate. Only Wenling Huang, who worked on this with me, she can calculate that by hand. Other people need tools for that. And in the end, you would come to formulas giving input equivalence classes. And the idea is if you apply certain sequences of simulations to your system under test, where you cover all these input equivalence classes in different order. And of course, these sequences have very special specification that I won't go into now. Then you come up with a complete test suite with a very strong one. And so here for our example, we have just one stable state where we wait for the next cycle. And then we go through transient states where all these calculations are done. And the states we are talking about are the control state, then the value of the actual value of the number of position estimates we have, the value of the confidence variables, and so on and so on. So this is our system state. And then, for example, if we wish to create a test step that leads us through a special path of transient states, we can automatically derive the conditions from the guard conditions, from the assignments in the different states. And then you get very refined conditions about how to set up your input values. And so this is the refined thing about the agents delivering inputs to the system under test that have been suggested by Kerstin Eder. I would refine what these agents do by covering these different conditions. And they can be enumerated. Of course, there's a finite one. And then you take your SMT solver and solve C1, get solutions for C1 and C2 so that this inequation holds and that inequation holds and so on and so on. And this leads you to a complete test suite that gives you the expected results. So your test oracle knows what to do and everybody is happy. So summarizing, the testing environment should cooperate, all the agents in the environment should cooperate to stimulate the system under test in such a way that the physical laws are obeyed. Of course, the agents must deliver position values that correspond to the actual speed and acceleration and to the last position value. Otherwise, you get invalid test cases that are not very informative. But within the boundaries of these physical laws, you would want to create sequences that cover these different classes in different orders. And this now, and then the theory says this guarantees that you will get the interesting testing situations. And so summarizing to that step here, and I'm nearly done with my talk. For the simple type of agent-based controllers that can be transformed into like UML state machines, then we can refine that suggested agency-based testing approach with such a complete testing theory, and you will get very strong test cases. And this question, have we tested enough? Can we have confidence in these tests? Can be answered in a good way. You can get certification credit for that. Now, I think the last two slides that I will show you that are worth discussing is what we cannot do. What am I afraid of at the moment? In general, you can program agent systems where a remote agent activates plan execution in our agent. And this is quite practical in some situations, but this dynamically creates a new thread in our agent so that several plans are now executed concurrently, which would not be so bad if this activation would not be dynamically. So at any moment, such a thread might be created and then it terminates at any other moment and so on and so on. Then it becomes harder when new agents may enter the game. Then you get a dynamic configuration change and you get new communication possibilities for your agent. And then everybody knows from theory, if we have dynamic creation of new communication channels, we are in the semantic expressive, we need semantics expressiveness of something like the pi calculus or an equivalent semantic model. And this is just another way of saying things become damned hard if you get dynamic configuration changes with new communication channels. And so, and it becomes even worse on the next slide. Even plans can be communicated by other agents. And then this good old idea that we had in the Lisp programming language, that you can treat code as data, comes up again, namely, one or two or three agents might together create a new plan as a text at runtime. So they invent a new recipe how they should solve a previously unknown problem. And then they exchange that as a real plan. And this is where things become really terrible. But I'm sure this will be happening in the future because it's such a wonderful idea that different agents can meet to solve a previously unknown task. And they will do that in the safety critical systems domain because it's so practical if they could do that. And from the formal methods perspective, that's a complete nightmare, at least as I'm concerned, because all these ideas of type certifications, where you check once and for all that the agent will execute everything properly in the future, you can't do that anymore. But fortunately, and this is what our research projects are about, there seems to be a way out. The most promising one is advocated by several authors. You do runtime acceptance testing and runtime certification. So two drones meet and they say, oh, we could lift this heavy Bentley together. And then they work out a plan how to do that. You go front, I take the back. And then they store this plan at a certification authority and do some acceptance testing. So this would look in the end as if this newly created plan has always been programmed inside these two agents. And then they run an acceptance test. And I think that would take too long to run it on the drone itself. So perhaps we would run that in the cloud in a trustworthy simulation environment. And there we would run 2 million tests in 50 milliseconds on 2,000 CPUs. And out comes, this plan has been nicely elaborated. Everything worked out nicely. And so the rely guarantees of the agents, the plans and the acceptance testing result would be documented at a certification authority, and then they go ahead and ship the Bentley right into the river next by. And so this might be a way to come out, to come around these problems that I see with these agent-based systems. And now I have made all the important points that I wanted to make. So excuse me that I skip these things and I stop here and leave some room for questions. Thank you very much for listening, though I could not see your faces. Perhaps everybody who went to sleep could raise her or his hand. Thank you very much.
Thank you very much, Jan. We have time for questions. Are there any questions from the audience? Yes, there is a raised hand. Kirsten, please go ahead.
Cool. Hi, thanks very much for such a cool talk. This is really cool. It does some of the things that are on our agenda in a slightly different way, not surprisingly. I think there is interesting overlap between what you've presented and where the challenges are actually. I think there are a few challenges we've identified that would fit into what you've presented, because I think in such a simulation environment, for instance, it's not just a question of whether you run all tests or not. It's also going to become a question of in which order you run them. Because if you can identify which of your tests dismiss the problem, say, no, this won't work, you would want to run them first. And so there might well be an ordering problem that is pretty useful.
Yes.
And it's not a problem now, but it is a problem when it comes to doing it online, because every second matters. But yeah, so the whole agent paradigm to use the agents in the test environment is actually not just for, I think this is not just for the sort of safety critical systems. I think there is much bigger scope for this. And I really like the connection to the formal methods, these sort of state machines. That's really nice. Are you thinking of rolling this out beyond the safety critical sector?
Yes, we have verified systems as a project partner there, and they will be commercializing these ideas, and also for non-safety critical things. But from our research perspective and from the Airbus perspective, the main focus right now is on safety critical things.
Yeah, really cool.
And just a side remark, you are completely right. One would like to have the failing tests first, or the most critical ones. There's an interesting idea. If you know the risk involved with different test cases, then you could do the test cases related to the highest risks first. And so there's a completely new topic to be opened, that you relate test cases to the risks involved, and then you do them first. And that might be an interesting result.
Absolutely, I fully agree with that. It's labeling test cases with everything we know, as much as is reasonable, so that we can select them, the most relevant ones for the question we are asking. And you might be getting away with a set of tests that is a subset. So you might find the answer to your question with a subset of the tests that you've got, because you've got the tests and you've got the labels at design time, and then you only need to pick the ones that are sufficient. So that's a new problem that we didn't have before. as far as I know. This is also very important for security and for online detection of security breaches or cyber attacks, as well as for determining the impact of a possible cyber attack. I'll be talking about this on Monday.
Okay, thank you very much, Kirsten. Are there any further questions? By the way, if you have a pointer to the talk you're giving, we would be very happy to advertise it in our mailing list so that people can learn more about.
Resilience node.
Oh, okay, yeah, okay, yep. We will definitely advertise it further. Good. Any further questions? So Jan, if there are no further questions, I could ask one question about uncertainty in the agent's belief. If the agent doesn't know exactly what the value of the sensor is, but knows it within a certain range, or maybe even knows something with its certain probability distribution. We have been discussing earlier today with people from Resilience Node and also with Jim this issue of uncertainty. Have you looked into making complete tests that can make claims about those uncertain aspects?
Not yet. We are not we are not experts in the statistical testing, but this might be something where we perhaps learn from your project in the future, because I understand that this is important, but at the moment we have not yet looked into that.
I mean, we could start with plain intervals and then look at more probabilistic extensions.
Yeah.
Oh, okay. Anna, you have a question?
Yes, please. Hello, Jan. Thank you very much. Nice to see where your work is at the moment. Is my interpretation right that what you achieve is a semantics based on state machines of the BDI language that you chose? And if so, how much of that language did you cover? Is that the vision that you have, picking up that language to describe tests as agents, describing them as state machines, and therefore then you drop into the theory that you already have? It's very comprehensive and neat for state machines. Is that the formal approach?
We will be discussing that in the future with the different application developers. So with people from Airbus, and we would also like to get input from your system developers. What would be the typical representation of your agent? My idea, my feeling is that if you are developing agents for robots or other autonomous systems, you would not like to represent everything in state machines, because these syntactic constructs like exchanging plans by sending messages and so on, they are so helpful that one could say, I rather take such a program as a reference model, though in the end I'm implementing that in C or C++ also, but I'm taking this as a model. And then we would translate that internally to internal state machine representations. But of course, we can't do the exchange of recipes, of the exchange of plans and the creation of plans. There we would not test, but instead we would wait until they have exchanged the plan. And from there, we would do this acceptance testing and runtime certification.
Right. Okay.
Okay. I think we are running gradually out of time. So I'm sure if there are further questions, we can reach out to Jan
Of course,
using email. And Jan is very kind to be present in several of our meetings, so we will hopefully have a chance to meet him, hopefully even in person, and have a chat further. Thank you very much, everyone, for being here for this edition of Verifiability Talk.